right, we are measuring the dimensions, and so to this point here, we're at 43, no wait, that's 43 inches at 109 centimeters, and height, our tallest item on here is here at 58 centimeters, and our depth is from here, it's actually from the outside edge of the wheels to the outside edge, and that is 57 centimeters. All right, the robot is weighing in at 52.22 kilograms.
We are excited to show the University of Nebraska Lincoln's proof of life for the NASA Lunabotics Lunar Rover competition for 2022-2023. The earlier clips we showed you include the weighing and sizing of our competition rover, certified by our advisor, Professor Karen Stelling. So as you can see here, the drivetrain is moving slowly through the sand material. We're using our sand volleyball courts because they are the closest way we can simulate lunar soil. So in terms of this slow movement, we're looking into using more powerful motors. These are things we'll be looking into between now and our presentation and demonstration, as well as when we compete in May. So with stronger motors, we hope to have more power and torque in order to really be able to easily navigate through the sand and other fine materials. So we weren't able to very easily navigate through craters and boulders with this current setup, but there are changes in progress for how to fix this for the future. So once we make these changes, we're sure we'll be able to accommodate for bigger craters and boulder obstacles, which will be implemented between now and our test readiness review. So this competition we're showing here is actually 14 minutes and 26 seconds without our certification videos, so we're speeding it up to 1.25 times speed to allow for enough time for the certification videos within our 15-minute time limit. So now that we've crossed into the mining zone and reached where we have dug and put rock under the surface, we put rock 30 centimeters under the surface of the sand, we're going to begin the digging process. So in terms of what we have for our excavation system, first off we have our linear actuator, which is what is tilting up the excavation system right now. So that needs to tilt up to 90 degrees so that it is directly upright before we then begin to move down the carriage. The carriage is running along 2 lead screws. So as we do that, we're also running our sim motor just a little bit to dig up the rock and allow for room for, as we lower that carriage, for the auger to sit. Otherwise, we're just putting a lot of pressure on the system. So once we're down to below those 30 centimeters of sand, we just run our motors and try and dig up as much rock as we can. As you can see, we're flinging up some rock, some of which is going into our system. So one of the really nice things about our system is that we've included an option to change the power of the auger motor based on a switch on our controller. So this means that we can be more precise if we see that we're not giving it enough power to be able to pull up the rock. We can give it a little bit more, but also if it's a little bit too powerful for what we're looking for, if it's flinging rocks too much, we can also just lower that down a little bit with that. So as you can see, we're now reversing the process to put away the excavation system. So that means we're pulling back up on the lead screws to bring the auger back up, and then now we're using the linear actuator to tilt the system back down. So we can't drive while that's up, we had to put it back down. But since our depositing system is on the other side, it works really nicely that we don't have to turn around 180 degrees to head back. We can just start driving backwards. So as you can see, we're about to begin navigating back to our sieve. So in terms of the systems that we use, we have all of these physical systems. We also have an Intel RealSense camera, which we use for image data from the robot. So our image data, we can return black and white as well as colored images and depth images based on what we want. And as stated earlier, we have some encoders for our motors, which is the reason why we used some weaker torque Go Build-A motors for our drivetrain, which we're thinking about changing to get the extra power we need. But we've really focused on having encoders on most of our motors this year. This will allow us to start working on how we can integrate autonomy into our robot operations. So the primary system we'll be thinking about automating first would be our hopper system. So we will use encoder feedback to try and figure out where our motor has rotated to, where it was coming from, and kind of determine where the systems are and whether they have been or have not been fully deployed. So we're just going to navigate back through, and then when we get back to our sieve that we have, we will begin the depositing process. So one thing to note is that we do not have every portion of our system set up yet. So one of the things we're still putting together is the kind of extra motors. So this year we were focusing more on adding extra features and just putting more consideration into each of the designs. Last year we were focused more on the simplest subsystems we could make that would get the job done. So some of the extra features that are still in the works that haven't been fully implemented yet are the vibrational motor on the hopper arm. So what you'll see later is that when we are working on depositing the rock, we pull, the pulley gets tightened and rotated, and then the hopper arm will come up and hit the shelf, depositing the rock. The issue is that there's a little bit of space on the hopper where rock can get stuck. Instead of actually coming off of the robot, off the hopper, and falling onto the sieve or shelf, instead it'll just sit there in the stuck area. So we have a vibrational motor on the hopper arm underneath it that could be used to kind of instigate a little bit of movement within the bin and make sure any extra pieces that are stuck will fall out. This hasn't been implemented yet, so as you can see here, when we begin the hopper depositing process, we still have a rock or two that we were not able to put on the shelf and was not weighed because it was not properly deposited. But so as you can see here, we've made it back to the depositing area. So in order to use our hopper, our auger and our hopper system are kind of reliant on one another. So since our hopper is kind of hidden away underneath our excavation system due to size constraints, we have to use the linear actuator to make sure our auger is up 90 degrees before we begin to use the hopper system. So as you can see here, we are tilting up the auger system, and then we're going to begin to use the hopper pulley. So as that works, you can see that there's some rocks that we dug up during our competition attempt that are in the bin, and as we pull up, they slowly fall out and nicely onto the shelf. But yeah, there were still one or two rocks that were not able to come out, and we kind of had to go back and forth a little bit. One of the big things to note is that this competition attempt, we only did one cycle of navigation, digging, navigation, deposit. And in our concept of operations, our plan is to do 3 cycles to make sure we get as much rock as we possibly can. So this wasn't possible at the moment due to the fact that we were having some drivetrain difficulties. It wasn't as powerful as we were hoping. So as we work on fixing those in the future, by the time we finish all our testing, we plan to have a system that can much quicker get through all of these obstacles so that it's a lot quicker. The biggest holdup with this competition attempt was just trying to get through the sand. So once we resolve those issues, we're confident we should be able to do the 3 cycles within one 15-minute competition attempt. Once the hopper is done, it lowers all the way back down, and then we lower the excavation system as well. And then after this, we have video of our advisor, Professor Karen Stelling, certifying the weight of the rock that we have mined. And that will be all for our proof of life video.
And then we're gonna put the rocks without sand.
It's very massive competition. The idea is it's a take down.
I have to,
Say how much it is.
yeah. So it says
About
72.
72.